What if I told you that everything you believed in was not true? Are you ready to admit that 2,000 years ago, without excavators, concrete mixers, or heavy trucks, the builders of ancient Rome constructed roads, aqueducts, and military camps at such an incredible speed that modern engineers would struggle to match their pace? This is not a myth or an exaggeration, but a documented historical fact that forces us to rethink the very concept of engineering genius. The Romans did not just build, they created the infrastructure of an entire empire capable of withstanding the test of millennia. And they did so with truly shocking efficiency. Watch the video to the end to find out how Roman engineers were able to stay ahead of their time and what the true secret of their construction supremacy was. I discovered this by accident while studying ancient maps and diaries. Have you ever wondered how the Romans managed to build roads at a speed of up to 5 kilometers a day without a single internal combustion engine at their disposal? Nowadays, such a pace of construction seems fantastic, but we are talking about roads, many sections of which are still in use today. The secret lay not only in the organization of labor, but also in the standardization of all construction processes, which the Romans brought to absolute perfection. The Roman road network, the famous Via Publica, was not just a set of trails, but a complex engineering system with a clear, multi-layered structure. First, engineers conducted surveys, choosing the shortest and most convenient route, after which legionnaires arrived on site to carry out the most difficult preparatory work. The road always began with excavation, which was carried out until solid ground was reached, and then huge stones were laid in the foundation to ensure drainage and stability. On top of this first drainage layer, called statumen, smaller gravel was poured and bound with mortar to form the second layer, rudis. The third layer, nucleus, consisted of gravel, sand, and lime mortar, which was compacted to an incredible density. In essence, it was a multi-layered highway with a perfectly designed drainage system that was not afraid of floods or harsh winters. Finally, the fourth layer, summum dorsum or pavimentum, consisted of perfectly fitted stone slabs that formed a strong and smooth surface. These slabs were laid with a slight slope from the center to the edges, so that water would quickly drain into roadside ditches, which significantly increased the road's service life. This system allowed the road to remain dry and usable in all weather conditions. To ensure such speed of work, the Romans used military labor rather than slave labor, which gave the construction process incredible discipline and coordination. Legionnaires were versatile soldiers, capable not only of fighting, but also of building, and each unit acted as an independent, highly efficient construction crew. For the legionnaires, road construction was part of their combat training and a way to maintain discipline in peacetime. Each legion had a whole staff of engineers, surveyors, and craftsmen who were fully responsible for the quality and speed of construction in their area. The use of standardized tools and standard building blocks, which were often prepared in advance, eliminated any delays associated with material shortages or rework. In addition, special tools were used in road construction, such as groma for laying straight lines and levels for leveling the surface. Engineers used special equipment to measure distances. An odometer, which was a chariot with a gear transmission that counted the distance traveled. This allowed them to control the length of the route with high accuracy and plan future stages of construction. Thanks to this, the roads were surprisingly straight and did not deviate from the specified route. This level of organization, standardization, and discipline, achieved 2,000 years ago, is a striking example of engineering management that far surpasses modern projects. For the Romans, road construction was a strategic military undertaking, not just a civil project. Indeed, a Roman road is not just a path, but a frozen-in-time manifesto of imperial power and engineering thought. Thanks to this phenomenal approach, Rome was able to cover the vast territory of its empire with a network of roads totaling more than 80,000 kilometers. These roads not only ensured the rapid movement of troops, but also stimulated trade, becoming the basis for economic prosperity. We are very interested in hearing your point of view. Write about it in the comments. Want to know the main secret of Roman durability? If roads were the arteries of the empire, concrete was its skeleton, and it was in this area that the Romans achieved perhaps their most impressive results. Roman engineers understood that the strength of the state depended on the strength of its buildings, so they paid special attention to materials and technologies. Their approach combined observation, experience, and the ability to work with the natural resources available around them. Thanks to this, architects were able to construct buildings that not only fulfilled their functions, but also survived the centuries. Even in ancient times, travelers marveled at how sturdy these structures were, and today we continue to experience the same feeling when we look at the surviving monuments. Roman concrete, known as opus cementitium, proved to be so strong and durable that many structures built from it, including the Pantheon and numerous aqueducts, still stand today, despite earthquakes, climate change, and the effects of time. It was a material that combined ease of preparation with incredible resistance to destruction. Modern concrete often begins to crumble after only a few decades because its composition is designed for different conditions and is built on different principles. Roman concrete, on the other hand, became stronger with each passing year, making it a unique phenomenon in the history of construction technology. Watch the video to the end to find out why modern scientists still cannot fully replicate this material and why its structure remains a subject of study. A key component of Roman concrete was a special type of volcanic ash called pozzolan. It was mined in the vicinity of Naples, where volcanic activity had left rich deposits of minerals. This ash had unusual properties, which the Romans noticed by observing the behavior of natural materials. Unlike ordinary sand, which is used in modern concrete and does not undergo deep chemical reactions, pozzolan formed a special binding agent with lime. This mixture became very dense and resistant to external influences. It did not crack as quickly and did not deteriorate under the influence of moisture. Thanks to this, concrete could stand for centuries, even when exposed to the open air. The pozzolan mixture was ideal for construction in regions with high humidity, frequent rainfall, and sharp temperature changes. It allowed the creation of walls and foundations that did not spread or crumble even in harsh climatic conditions. But the most impressive thing was that this mixture was resistant to seawater, which is one of the most destructive factors for building materials. The Romans could build ports and harbors without fear that their structures would crumble under the influence of salt water. This gave them a huge advantage in expanding maritime trade and their military fleet. The main difference between Roman concrete and modern concrete was its ability to self-repair. This quality has only recently become known. When scientists studied the structure of ancient samples under a microscope, they discovered small pieces of quicklime in the concrete, which were activated on contact with water, filling cracks that had formed over time. This reaction occurred naturally, without human intervention. When moisture penetrated the concrete, new calcium carbonate began to form, which literally sealed the damage. Therefore, the walls and foundations did not collapse, even if cracks appeared in large numbers. This process was called the secondary growth effect because new crystals were continuously forming inside the material. This turned concrete into a living structure that could respond to changes in the environment. Modern materials do not have this ability, so they require regular repair and maintenance. Roman concrete, on the other hand, worked with virtually no human intervention, making it ideal for large-scale construction projects across the empire. This allowed for the creation of structures that survived in conditions where other materials would have collapsed within a few decades. The Romans did not use rotating concrete mixers to prepare concrete because such technology simply did not exist. They mixed the mortar by hand, often in teams using large pits or specially paved stone areas. The work was hard and required a lot of experience, but it made it possible to control the composition of the mixture and avoid mistakes. Roman builders knew how to achieve the desired density and uniformity of concrete and paid attention to every detail. They understood that the durability of a structure that could stand for centuries depended on the quality of the mixture. The prepared mortar was then poured into wooden formwork in layers. Each layer was tamped down to remove air, because voids could weaken the structure and lead to destruction. As a filler called commenta, they used pieces of stone, broken bricks, or even fragments of ceramics. These materials not only made the concrete stronger, but also helped to save resources because they could be collected at the construction site. This mixture became very rigid and was ideal for creating massive walls and foundations. The Romans also developed a special type of marine concrete, which was a real engineering breakthrough. It allowed them to build sturdy piers, breakwaters, and ports directly in the water. This concrete could interact with seawater in such a way that it only became stronger. As the waves washed over the structures, new minerals formed inside the material, strengthening it. Thanks to this, Roman harbors could serve for centuries, even when exposed to constant storms. The use of opus cementitium allowed the Romans to abandon complex stone masonry, which required a lot of experience and time. Monolithic structures were erected faster, were stronger, and required fewer workers. This is particularly evident in the example of the Pantheon. Its dome remains the largest unreinforced concrete dome in the world, and to this day, no one has been able to replicate it completely. The Romans used different fillers at different levels of the dome to lighten the upper part of the structure and reduce the load. But have you ever wondered how the Romans built their famous aqueducts, delivering water hundreds of kilometers without using pumps? Are you ready to learn the secret of how simple water became the foundation for building an entire empire? You've definitely never heard of this unique secret. Military camps, or castra, were no less impressive examples of Roman construction speed. A legion, which could number up to 6,000 men, was capable of erecting a fully fortified, standardized, and functional camp in just a few hours. It was not just a place to sleep, but a real temporary fortress that provided security and order for the troops. Liking this video will help it get more views. The process of building a camp was automated and subject to strict regulations, which were strictly observed by every legionnaire. First of all, surveyors used a groma to mark out the territory, determining the location of the main streets and gates. The camp always had a rectangular or square shape, and its layout was absolutely identical, regardless of the terrain. Construction began with the digging of a defensive moat, fossa, and the erection of a rampart, agger, from the excavated soil. This was the first line of defense, which was built at incredible speed using standard tools, shovels, pickaxes, and baskets. Then a wooden palisade, vallum, which each legionnaire carried with him, was installed on the rampart. Inside the camp, tents, barracks, headquarters, a hospital, warehouses, and a parade ground were arranged in a strict grid pattern. Each unit knew its exact location, which eliminated chaos and confusion. This standardization allowed the troops to feel at home wherever they were. The headquarters, or principia, was located in the center of the camp at the intersection of the two main streets, the Cardo and the Decumanus. It was the administrative and religious center, as well as the place where the banners and treasury were kept. From here, officers could effectively manage the entire camp. Prefabricated elements were used for quick construction. For example, wooden supports for tents, ready-made structures for watchtowers, and elements of the palisade. All this was transported together with the legion, which eliminated dependence on local resources. The camp was always designed with hygiene requirements in mind. Sewage and wastewater disposal systems were mandatory elements. Garbage pits were located away from residential areas, and baths, thermae, were built to maintain the cleanliness of the legionnaires' bodies and spirits, which was critical to preventing epidemics. Order and discipline were so strict that even tents were set up in a straight line, and all property was stored in strictly designated areas. This routine and predictability were part of the legionnaires' psychological training, which helped them maintain their fighting spirit. The camp was a symbol of order and civilization in the midst of hostile territory. The legion's ability to quickly establish a fortified home in any territory was a huge tactical advantage. It allowed them to act aggressively and not fear sudden attacks at night. Thus, the castra was not just a temporary shelter, but a model of field engineering, combining speed, functionality, and safety. They are a striking example of how standardization and discipline can ensure incredible efficiency in construction, surpassing many modern approaches. It was a true triumph of military organization. Like this video if you like the facts we're talking about, and be sure to subscribe to the channel so you don't miss new videos about ancient Rome. What you are about to learn will change your perception of ancient hydraulic engineering. Roman aqueducts are considered one of the most recognizable symbols of ancient engineering genius, but their true complexity lies not only in the monumental stone arches that amaze tourists. The main secret is hidden in the accuracy of the calculations that Roman engineers achieved without modern instruments. They worked without optics, laser levels, or electronic measuring devices, yet they managed to lay water pipes for tens and even hundreds of kilometers so that the water flowed naturally. Their system relied solely on observation, experience, and the ability to work with the natural terrain, which makes the result even more impressive. How did the Romans achieve such precision without modern technology or sophisticated tools? To begin with, engineers used special devices created exclusively for hydraulic engineering tasks. One of the main ones was the corybatus, a long wooden trough filled with water that functioned as a water level. This tool allowed them not only to set the slope, but also to check the evenness of large areas of terrain. The water itself showed even small deviations, which made the device incredibly accurate for its time. Roman craftsmen regularly checked the position of the trough, cleaned it, and moved it from place to place to achieve a perfectly straight line. Thanks to this, they were able to determine the desired slope with remarkable accuracy and adjust the route of the future aqueduct at the earliest stages of work. The main secret lay in the minimal but strictly maintained slope of the aqueduct. On average, aqueducts were designed with a slope of about 2 or 3 dozen centimeters per kilometer of the route, which is barely noticeable to the eye. Such a small slope ensured a uniform flow of water and prevented the destruction of the canal walls. If the slope was too steep, the water would flow too quickly, destroying the structure. If it was too small, the flow would slow down and could cause stagnation. Maintaining the ideal gradient over hundreds of kilometers required tremendous concentration, vast experience, and the ability to work in difficult terrain. Engineers had to take into account the slightest changes in elevation to ensure that the system worked without interruption. Laying the route was one of the most labor-intensive and intellectually challenging tasks. Engineers used a surveying instrument called a diopter, which helped measure horizontal and vertical angles and set straight lines. In addition, they used grommets, long measuring cords stretched over long distances. They carefully studied the terrain, identified all the depressions and elevations, and chose a path that would maintain a constant slope without sharp jumps. Their goal was to ensure that the aqueduct followed the most rational route, avoiding costly and complex work. Therefore, engineers often preferred to bypass hills and smoothly curve around uneven terrain rather than dig tunnels. However, sometimes tunnel construction was unavoidable, and then the Romans demonstrated their supreme engineering skills. Tunnels were dug simultaneously from both sides, with workers heading towards each other. This required extremely precise calculations, as any mistake could result in the passages not matching up or converging at the wrong angle. Despite this, surviving documents and archaeological research show that the Romans achieved a convergence of tunnels with an error of only a few centimeters. This is an amazing result, especially considering that the entire process was carried out manually by the light of lamps and torches. Maintaining the specified slope in a confined space made the task even more difficult, but Roman craftsmen coped with it thanks to their experience and precise measurements. In places where deep valleys or wide rivers prevented them from maintaining a constant slope, the Romans built their famous arcades, rows of stone arches. These structures raised the aqueduct to the required height and allowed the water to flow smoothly. The arches were both strong and economical because their shape provided stability with minimal material consumption. Roman architects masterfully used the properties of arch construction, allowing the canals to cross difficult areas without significant differences in height. In addition to their practical benefits, the arcades created impressive visual lines that still inspire admiration and adorn the landscape. What if I told you that one of the largest structures in history was built without modern technology? The Colosseum, or Flavian Amphitheater, still amazes with its size and structural complexity, but even more impressive is the speed with which it was built. This monumental structure, capable of accommodating up to 50,000 spectators, was built in just 8 years, which in our time is an unthinkable period even for less complex projects. It was not just a building, but a symbol of the empire's engineering and construction triumph. Construction began around 72 AD and was completed by 80 AD. This speed was achieved through the standardization of all processes and the efficient use of various building materials. A strong foundation of Roman concrete was poured into the base of the Colosseum, which securely fixed the structure on unstable ground. The structure itself was built on the principle of rings and tiers. The outer walls and main supports are made of more durable travertine, a light, porous limestone. Standard blocks were used for quick and accurate masonry, which were delivered to the site in huge quantities. The interior walls and arches were made of light and durable brick in the same Roman concrete. The secret to efficiency was the division of labor and parallel work. The construction site was divided into many sectors, and in each of them, independent teams of masons, concrete workers, and carpenters worked simultaneously. This allowed construction to proceed around the entire perimeter without waiting for the completion of previous stages. Complex lifting mechanisms powered by human or oxen muscle power were used to lift heavy stone blocks and marble cladding. These were lifting cranes with winches, operating on the principle of a pulley block, which could lift loads weighing up to several tons. The Romans were masters in the use of levers and pulleys. The complex system of stairways and passageways inside the Colosseum, known as the vomitoria, was designed so that 50,000 spectators could enter and leave the arena in just a few minutes. This calculation of people flows, which today is called crowd control, was incorporated into the design from the outset and is the pinnacle of architectural logistics. Beneath the arena was the hypogeum, a complex system of underground tunnels, animal cages, and mechanical lifts. This underground factory allowed wild animals, gladiators, and scenery to be lifted into the arena in a matter of seconds, making the performances even more impressive. The hypogeum is an example of complex mechanical engineering. The Colosseum was also equipped with a retractable awning, the velarium, which protected spectators from the sun and rain. This huge canvas structure was set in motion by a complex system of ropes and masts operated by trained sailors. The velarium was another example of engineering ingenuity. Thus, the Colosseum is not just an amphitheater, but a triumph of Roman engineering organization. It is a symbol of the empire's ability to mobilize resources, standardize processes, and use the latest technologies to achieve unprecedented construction speeds. It was proof that with the right organization and discipline, manual labor can be incredibly effective. Ready to learn a secret that will change your life? For the Roman legions, construction was inextricably linked to warfare, and their engineering superiority often determined the outcome of campaigns. Their ability to quickly erect temporary bridges, siege engines, and fortifications allowed them to maintain the initiative and strike where the enemy least expected it. In this chapter, we will look at the most impressive examples of their military engineering genius. The most famous example is Caesar's famous Rhine Bridge, which was built in just 10 days in 55 BC. It was needed to transport legions to the eastern bank of the Rhine to strike a blow against the Germanic tribes. The bridge was built from wooden piles that were driven into the riverbed using special hammer drills powered by cables and winches. The bridge's design was ingeniously simple and resistant to the current. The piles were driven at an angle against the current, and then another pair at an angle with the current, creating a strong and reliable V-shaped connection. Beams and planks were laid on top of them to form the roadway. This technology allowed bridges to be built incredibly quickly. The legions always had engineers who specialized in the construction of siege engines. Ballistas and catapults were not just throwing machines, but complex engineering structures that were assembled directly at the siege site from pre-prepared parts and local timber. Each machine was assembled according to drawings and standards, which ensured their reliability and power. To capture fortified cities, the Romans built siege towers, or turmi. These huge, multi-story wooden structures on wheels were taller than the fortress walls and allowed legionnaires to fire from above and directly attack the enemy walls. Turms were assembled from standardized wooden sections that were prepared in forests and transported along with the army. Another example of their speed of construction is the erection of siege lines. For example, during the siege of Alesia, Caesar's legions built 2 lines of fortifications, an inner line to protect against the besieged and an outer line to defend against the approaching Gallic reinforcements. These lines, which included moats, ramparts, towers, and traps, were erected in just a few weeks. A variety of traps were used on these siege lines, such as lily, pits with sharpened stakes, and stimuli, sharp wooden spikes that slowed the enemy's advance. This was not only construction work, but also engineering work, which required high precision and coordination. All these projects demonstrate that the Roman army was not only a fighting force, but also a construction machine. Each legionnaire was a versatile specialist, capable of turning a clear field into an impregnable fortress or building a road through a swamp in a matter of hours. Military engineers, or fabri, were among the most respected and highly paid specialists in the army. Their engineering skills were so advanced that they could adapt to any terrain and quickly find a solution to any problem. Their ability to build quickly, reliably, and in accordance with strict standards was their main secret to success. Have you learned how the Romans used their military skills to create the most powerful construction projects? The success of Roman construction cannot be explained solely by the genius of individual engineers or the talent of outstanding craftsmen. It was based on total, almost maniacal standardization and unification of all construction elements, technologies, dimensions, and organizational processes. While modern architectural projects often strive for uniqueness and require complex individual calculations, the Romans chose the opposite path, creating universal templates that could be reproduced anywhere in the empire. Thanks to this, there was no need for lengthy calculations and adjustments at the construction site. Everything had already been determined in advance. Virtually the entire Roman construction industry operated on the principle of pre-prepared materials produced in standardized sizes. Bricks, stone blocks, tiles, roof tiles, wooden beams, everything had clearly defined parameters. This made it possible to produce and store building elements in huge quantities, transport them across the empire, and use them without additional processing. In essence, the Romans created a prototype of the modern conveyor system in which workers acted more as assemblers than craftsmen, and the construction site became a place of assembly rather than manufacture. Even the dimensions of the bricks were regulated with astonishing precision for the ancient world. There were different types of bricks, for load-bearing walls, for cladding, for arches, and for decorative elements. Bricklayers could work incredibly quickly because each element fit perfectly into its place without the need for adjustment or trimming. This system greatly reduced the likelihood of errors and accelerated the process of constructing buildings, aqueducts, baths, bridges, and military fortifications. Standardization did not only apply to bricks. Road paving slabs, once to the famous aggers, also had standardized dimensions. This ensured their tight fit, even load distribution, and high durability. Roman roads hardly settled and did not collapse due to gaps where water would accumulate. Where other civilizations would have faced swelling, cracking, and erosion, Roman highways retained their strength for centuries. The use of uniform sizes and laying techniques was critical for infrastructure stretching thousands of kilometers. The unification of the measurement system was no less important. The entire Roman construction world was based on the pes, the Roman foot, and the mille passuum, 1,000 double steps, or a mile. This system was uniform throughout the empire, from Britain to Syria, from Egypt to Gaul. Any engineer or builder who looked at a drawing could be sure that these measurements would be understood and applicable in any region. Given the vast territory, this provided remarkable opportunities for coordinating projects. Even the tools were standardized. Surveying instruments, water levels, plumb lines, measuring rulers, and squares were all made according to uniform standards. Legionary builders and civilian craftsmen used the same tools, which eliminated differences in the accuracy of markings. Thanks to this, the Roman army was able to build roads and forts with the same speed and accuracy as professional civilian architects. The system of drawings and project documentation was also standardized. Roman engineers used graphic plans, sections, and diagrams that were understandable to any trained builder. This made it possible to transfer projects between provinces without wasting time training local craftsmen in the specifics of the layouts. The principle of standardization also applied to military construction. Details of siege engines, elements of camp fortifications, wooden towers, ballistas, catapults, legionnaires' tents, fasteners, and even some personal equipment were produced according to common templates. This offered enormous advantages. A legion could quickly replace a damaged part, assemble a siege engine on the spot, or erect a fortified camp in hours rather than days. Standardization turned the army into a well-coordinated mechanism capable of operating anywhere in the empire. It was thanks to this comprehensive unification that the Romans achieved incredible construction speeds. They did not have to reinvent technology for each project. They assembled structures like a set of standard, time-tested blocks. It was a truly industrial approach long before the advent of industry, allowing roads, aqueducts, walls, and cities to be built with an efficiency that Europe would not see again for many centuries. Despite the absence of sophisticated engines, the Romans were masters at using mechanical advantages to lift heavy loads. They developed a whole arsenal of lifting mechanisms powered by muscle power. These were not just primitive devices, but complex systems based on a deep understanding of physics. The basis of all lifting devices was the pulley block, a system of blocks and ropes. The use of several pulleys made it possible to greatly reduce the effort required to lift a heavy load. This allowed several workers to lift stone blocks weighing several tons. The most common lifting device was a trispaston, a crane with 3 pulleys powered by a winch. For heavier loads, 4 and 5 pulley cranes were used, which required more workers. To lift the heaviest elements, such as columns or capitals, a pulley block with a huge wooden wheel was used. Inside this wheel, which resembled a squirrel wheel, were workers who walked around, turning it. This device converted horizontal force into vertical force and was capable of lifting loads of up to 30 tons. This entire system required perfect coordination and synchronization of effort. The workers had to act in unison, on command, to avoid load imbalance and accidents. It was a complex choreography of manual labor that required discipline. Special metal clamps were used to position the heavy blocks accurately, which were inserted into holes made in advance in the stone. These clamps, called forcipes, allowed the block to be securely fixed and lowered into place with precision. When constructing buildings with massive walls and arches, the Romans actively used temporary wooden structures, scaffolding, and formwork. Scaffolding allowed workers to work safely at height, and formwork served as a mold for pouring concrete and a temporary support for stone arches until the mortar set. Carpenters were among the most sought-after specialists. They not only made formwork and lifting mechanisms, but also built temporary dams and embankments during the construction of bridges and ports. Their work was no less important than that of the masons. Thus, Roman manual labor was highly technological. They did not simply lift stones, they used mechanics to multiply their muscle power many times over, which allowed them to achieve such impressive results. It was a triumph of simple engineering. One of the key factors that ensured the incredible speed of construction was confidence in the quality of the materials used. The Romans had strict quality control at all stages of production, which eliminated delays associated with defects or the need for rework. They understood that durable materials save time in the long run. Limestone, brick, sand, lime, and pozzolan, all of these materials were extracted and processed according to strict standards. There were state-owned quarries and brick factories that supplied standardized products for large projects. This ensured not only quality, but also consistency of supply. Quality control was important, first and foremost, for lime, which was the basis of the cementitious mortar. The lime had to be well burned and then properly slaked. The process of burning lime in kilns required strict adherence to the temperature regime, which was controlled by experienced craftsmen. Roman concrete itself, as already mentioned, was not just a mixture, but a complex composite material. Engineers carefully monitored the proportions of the components to ensure maximum strength and water resistance. Each type of structure used its own optimized concrete composition. The durability of Roman structures can also be explained by their deep understanding of drainage. All their structures, from roads to building foundations, had a well-designed water drainage system. Water is the main enemy of any building material, and the Romans learned to combat it effectively, prolonging the life of their creations. The use of multi-layered structures in roads and foundations was aimed at preventing capillary moisture absorption and freezing. This allowed the load-bearing elements to remain strong even in the harsh climatic conditions of the northern provinces. The Romans also skillfully used various types of masonry, opus. For example, Opus reticulatum was masonry made of small, pyramidal blocks, which was not only beautiful but also economical. Opus incertum, an earlier type of masonry made of uneven stones, was used in less critical structures. Thus, the speed of Roman construction was not only in the rapid erection of buildings, but also in the fact that these structures required virtually no repairs for many centuries. The inherent quality of the materials and construction made it possible to avoid costly and labor-intensive maintenance. Ultimately, the most important secret of Roman construction speed lay not only in technology and standards, but in their outstanding ability to manage projects and mobilize human resources with such precision that it was as if they were operating a machine. The Romans transformed construction from a set of disparate craft practices into a highly organized, centralized, and almost industrialized process. It was a true triumph of administrative efficiency, with every action, every worker, and every tool occupying a strictly defined place in a vast system. All significant state construction projects were under the control of the central authority, the emperor, the Senate, or special construction commissions. This vertical management structure ensured the timely allocation of funds, strict adherence to schedules, and an almost complete absence of bureaucratic delays. In Rome, it was understood that roads, aqueducts, fortresses, and harbors were not private initiatives, but infrastructure arteries on which the functioning of the entire empire depended. Therefore, construction issues were resolved quickly, decisively, and with full awareness of their importance to the state. On site, construction work was supervised by highly qualified engineers and architects who combined technical knowledge with administrative skills. They were responsible for the entire cycle of work, conducting research on the site, developing the project, preparing estimates, allocating resources, organizing work crews, quality control, and final delivery of the facility. Such a specialist was simultaneously a mathematician, manager, engineer, inspector, and accountant, a figure of a completely special level of training. The Romans mobilized human resources with remarkable flexibility. Legionnaires served as the main workforce for state infrastructure projects. It has been proven that their discipline, physical training, and ability to work in a coordinated system made them indispensable builders. In a matter of weeks, they could build forts, ramps, bridges, temporary roads, and entire camps, all according to pre-established standards. Their organization ensured a pace of construction and precision of execution unheard of in antiquity. Private contractors were hired for civil projects, but they were also required to strictly adhere to state construction standards and work under the supervision of imperial engineers. There was competition between contractors. Those who built better and faster received new contracts, privileges, and financial benefits. This created a powerful incentive for efficiency and accuracy. The Romans applied the principle of the assembly line in one of its broadest meanings. Any project was broken down into dozens of simple operations that were performed in parallel. One group cleared and leveled the ground, another mixed opus cement, a durable Roman concrete, a third installed formwork, a fourth laid stone slabs, and a fifth did the finishing work. This organization completely eliminated downtime. While one team was performing its part of the task, another was already ready to continue the work. This approach greatly increased efficiency and allowed huge projects to be completed in the shortest possible time. The material supply system was also carefully organized. Deliveries of stone, wood, bricks, metal, and tools arrived at exactly the right moment. Not too early, so as not to overflow the warehouses, and not too late, so as not to slow down the construction process. Roman engineers were masters of logistics. They knew how to plan supply chains covering tens and hundreds of kilometers, taking into account seasonality, road accessibility, the speed of carts, and even route safety. We conclude our immersion into the world of Roman engineering genius. These people, with nothing at their disposal but the strength of their hands and ingenious minds, were able to erect structures that have survived for millennia. The Romans proved that true speed of construction lies not in the power of machines, but in the perfection of organization, the quality of materials, and the accuracy of calculations. Their concrete, their roads, their aqueducts. All of this is silent testimony to the fact that engineering based on the fundamental laws of physics and mathematics is timeless. The lessons we can learn from their experience are still relevant today. standardization, a deep understanding of materials, and, most importantly, discipline and organization of labor. The Romans were ahead of their time, and their legacy continues to inspire us. Which of ancient Rome's engineering mysteries do you find most incredible, and why? Was it self-repairing concrete or the incredible precision of the aqueducts? Suggest topics for future videos you would like to see on our channel in the comments. And don't forget to subscribe so you don't miss out on new investigations into historical mysteries.